This is the solution to Chapter 14 video assignment 2. The question states, between 1993 and 1995, sodium phosphate was added to the Seathwaite Tarn in the English Lake District to increase the tarn's pH. Explain in some detail why addition of this compound increased the pH. Don't just say sodium phosphate is acting as a base. Clearly it is acting as a base. Explain in some detail all the reasons why it is acting as a base. So the chemical formula for sodium phosphate is Na3PO4, and it dissociates in water according to the following reaction. Because sodium is a group 1 alkali metal, basically anything that anytime it makes a salt, anytime it's bonded to anything, it's going to be super soluble in water, right? So this is going to dissociate entirely into 3 sodium ions and a phosphate ion, because sodium is a group 1 alkali metal. So given that, we have to look at the 2 different ions that come out of this species to see how they're going to affect the pH. So first look at sodium. Sodium, to determine how it affects the pH, the easiest way is to just look at its conjugate base. And the conjugate base for sodium is sodium hydroxide, right? And we know that sodium hydroxide is a very, very strong base for many of the similar reasons that this dissociated in water. Because sodium is a group 1 alkali metal, this is going to dissociate entirely in water, according to this reaction right here. Sodium hydroxide is going to dissociate in sodium ions and hydroxide ions. So because sodium hydroxide is a very, very strong base, its conjugate acid, sodium, is going to be a infinitesimally weak acid. In other words, it's just going to be less effective than water at being an acid. So it's going to be essentially inert, a spectator ion. It's not going to affect the pH at all. The other species we have to look at here is the phosphate ion. Now, the conjugate acid for phosphate is phosphoric acid. Right, we have this -3 charge here. We can throw 3 hydrogens on there. Now I wrote the dissociation, it's a polyprotic acid, right? So it has the potential to lose all 3 hydrogens. So I wrote the dissociation reaction for each of those 3. Phosphoric acid is going to yield dihydrogen phosphate, I think that's what that's called. That's going to yield hydrogen phosphate, and hydrogen phosphate is going to yield phosphate as their respective conjugate bases. So essentially, from beginning all the way to end, phosphoric acid is going to yield these phosphate ions. And so they're the conjugate base to a very weak acid, or not very weak, but just a weak acid. Phosphoric acid is a weak acid. As you can see here, represented by their Ka values, which I got from handy Google search. So the Ka value for this first reaction is 7.5 times 10⁻³ and it just gets smaller and smaller. So because this is less than 1, we know it's a weak acid, and we know that weak acids have weak conjugate bases. So because of all that, we know that phosphate is going to act as a weak base. And so as a weak base, it's going to be accepting hydrogens. And as, according to this relationship here, right, Kw equals the concentration of hydrogen and hydroxide, as hydrogens go down, hydroxide is going to go up. And therefore it's going to become more basic, right? pH is represented as the negative log of hydrogen ions. So if the hydrogen ions are going down because this phosphate is accepting them, the number here, the negative number, is going to be bigger, therefore the pH is going to go up. So essentially that is why the pH went up when sodium phosphate was added to the lake.